So the outline for your test is posted on Canvas at the bottom of that, the Module 3B list of where the assignments recently have been. Covers everything since test 2 other than just strictly questions about what's the derivative of. We did that on the mastery test, so there won't be questions related to just finding derivatives other than implicit differentiation. So we will actually talk about part of what we're going to do on Monday, a cool way we can use implicit differentiation to prove some other things that some of our derivative rules, like related to logarithms, exponents, and power rule, that we just kind of estimated our way through those proofs, essentially, kind of like left out some details and said, this kind of makes sense. We will finalize that, talking about implicit differentiation on Monday, good review of that, as well as kind of tying up the year. But I do want to go through another related rates question, this one that I showed you at the end of class on Monday, and then also the two most common, at least we'll see if we get more time, two most common questions from the homework that you asked for were numbers 9 and 12. 12 most common, 9 second most, and the third place was number 10. So we'll see if we have time for number 10 or not, but I definitely want to go through those first two. Actually, one of them has a similar setup to this one, but it's an entirely different type of problem. So once you set it up, there's many different things to do. In any case, this question, we've got a streetlight at the top of a 16-foot tall pole, a woman that's 6 feet tall, currently 35 feet from the base of the pole, is walking away from it at 4 feet per second, and we want to know at that point, when she's 35 feet away from the pole, how fast the tip of her shadow is moving along the ground. So, in any case, let me get this going here. Alright, so I remember drawing a lovely picture for you before. Let me put this up here. So I've got a street light and a person walking away from it. We'll pretend that these are horizontal and vertical lines. Person is 35 feet away from this, not necessarily to scale here, but the idea is, again, if I have a street light, light goes in every direction, but when it goes towards where this person's head is, the shadow of her head is projected in a straight line, continuing down from there onto the sidewalk. Ooh, turned out to be a fairly straight line. So person's head here, there we go, now it's a person. In any case, this person is 6 feet tall, the street light is 16 feet tall, and we know that the distance between the person and the street light at some point in time is 35 feet. So we can use that later. I'm just going to use this because she's walking away. So this distance is increasing all the time. I'm going to set that, I'm just going to leave that as an unknown for right now. I'll call this x. And at some point in time, x is 35. But that distance is changing, so I want to be able to take a derivative of something with x involved. X is from here to there. That's 35. Now this distance is who knows what, but those two put together could form a side length. One of the legs of a right triangle goes with this 16. I'm going to call this distance, I don't know, A. I'd call it S for shadow, but my S's always end up looking like 5s, so I'll just leave it as A. So A is the length of her shadow. X plus A, and there's different ways you could set this up, would be the whole length here then. Now, I just kind of arbitrarily made that. I could have called this whole length X and made this something else, and that's, like have one of those be subtracted from the other. But those lengths are all related. At some point in time, X is 35. So I want to have some place to substitute that in eventually that's easy. What I'd like to know is actually how fast, let's see, how fast is the tip of her shadow moving along the ground? Well, the tip of her shadow is here, but it's what this is asking about. And here's where I'm going to, this is the reason I did this way, is because this is kind of a start way to set your problem up. There's lots of different ways you can start this. Some make it easier to work with than others. And if you start doing something and you realize, oh, this is going to be a weird expression, you can always change your variables and make it easier later. Like I said, this xa and x plus a, I could have written the whole thing as an x and something else as x minus a or something like that. Because thinking about how fast is the tip of the shadow moving along the ground, I want to have an expression for that. So how fast the tip of the shadow moving along the ground is. The shadow's moving out this way, but it's not just moving out in front of her. It's moving out, it's the whole length along the sidewalk. So I really want to know how fast the tip of her shadow is moving along the ground, so how long this whole x plus a is changing. Like, oh, I need to know a derivative of x plus a with respect to t. That sounds kind of weird. So if you do something like that, like, I don't like the way this is set up. Let me call this a simple variable. That's kind of strange. So instead of calling this x plus a, if we go back and say, you know what, let me make my variables easier to work with. Let me call this one, I'm going to use a different letter so I don't confuse my x's. I'm going to call this y. I'm still going to call this a. I don't need to know what a is in particular. And then this part would be y minus a. All right, so this is then y minus a. So if you set things up a couple of times to try it out, and it's like, okay, now I can see what my goal is. How fast is the tip of her shadow moving along the ground? That would be how fast this point here is going out that direction, not just how fast it's moving in front of her, because she's moving also. So if I just talk about how much the shadow moves out in front of her, that's going to be moving more slowly than how fast the shadow is moving along the ground. So not relative to a moving point, but relative to a stationary point, the streetlight. So I want to answer this question, how fast is the tip of her shadow moving along the ground? In this diagram, this is how fast is y increasing? Or in other words, find how fast y changes with respect to time. I'll just use t for time, and that's fairly common. Lots of times you'll see that in questions, examples. If you look up more examples online, just all of a sudden t is there. Like, what's t? With related rates questions, it just kind of all of a sudden gets inserted a lot of the time. Just think of that t, if you see it suddenly without explanation, as some sort of unit of time. Use whatever units are in here. And we've got feet per second, so okay, t is going to be time in seconds. The thing is, though, we're not going to need to substitute in a value for t or write an expression in terms of t at any point. We're just kind of imagining y as a function of t. A is also a function of t. Y minus a is a function of t. All of these things are. But the relationship between y and y minus a and this a all have to do with the fact that I've got these two intermingled triangles. I've got one triangle that fits neatly inside the other. They're similar triangles. They clearly share, if you want to go back to fun with geometry, they have a common angle here, and they're both right triangles. So they have two angles in common, which means the third angle must be the same, and so therefore all three angles, angle, similarity property, your geometry teacher would be happy if that sounds familiar to you. So in any case, these two triangles are the same ones, just scaled up from the other. Long story short. So if I have one triangle that has the streetlight as this corner and y, the length of the tip of the shadow back to the streetlight as its base, and a second triangle, I'm just going to draw it separately to kind of unconfuse these points. This has a as the base and 6 as the height. These two are similar triangles, and A, I know, is related to Y. I could talk about whatever. I could rearrange these letters again. Maybe I'm just going to call this like A and this Y minus A. Doesn't really matter. You can set this up however you want as long as you keep track of your expressions. So 16 and Y are related in the same way that 6 and A are. And so I don't have to, Y and A and X are kind of all over the place. I need y minus a to be 35. Let's see. A woman 6 feet tall walks away from the pole with a speed of 4 feet per second. Oh, 4 feet per second is the speed at which this is increasing. I don't like these like complex, that's a weird thing. So I'm going to change this again. I'm going to make this one y minus a, and this one just a. There. Now I can have simple expressions. So the things that I'm looking for, if they turn out to be messy expressions, you can change the variables. So this 4 feet per second, now it's dA dt. That's how fast she's walking away from this. and y, how fast are shadows moving, is dy dt. So now I've got y as the whole base and y minus a as this little base, which looks messier on the triangles, but that means that this length, which I know how fast it's increasing, just like the first time when we had it as an x, now that length is a simple like expression instead of being kind of a weird subtraction. If you don't like how your variables are, change them. So now I've got 16 is related to y in the same way that 6 is related to y minus a. And so this is an equation relating y and a. It's not solved for either one. You could take the derivative implicitly from this form, but I would suggest getting those variables up out of the denominator so you don't have to do anything like quotient rule. And in fact, if you cross multiply to simplify this, 16y minus a equals 6y. You can see that this equation simplifies down a lot. It's just a linear equation with y and a, and there's lots of canceling we can do, like 16y minus 16a. I can even just solve this for y. I don't have to do like messy implicit differentiation, but x and or a and y are both things that we are considering to be changing over time. They're both functions of time. So although I could simplify this maybe to 10y equals 16a, or y equals, dividing by 10, 1.6a. There, that's a nice linear expression. The derivative of y with respect to a is 1.6. The derivative of this expression with respect to time will help us solve the problem. So if I start from this nice simple equation, y equals 1.6a. Simple equation, took a while to figure out what it is. But if you can see in this equation, oh yeah, y is this length here. It's going to be 1.6 times what this is because of the relationship between these heights there. So in any case, if I have y equals 1.6a, then the derivative of y with respect to time, how fast the shadow's moving along the sidewalk, how fast the tip of the shadow's moving away from the streetlight, a stationary point, is going to be 1.6 times how fast a is changing with respect to time. A is how fast she's moving away from the streetlight. The distance between the streetlight and the person, how that changes with respect to time, the a dt. So y is 1.6a, and the rate of change is going to be 1.6 as much also of y in terms of how it's related to a's rate of change. So if I know that she's walking away from the pole at 4 feet per second, that's this length, the distance between d a dt is 4 feet per second. Then the rate at which the shadow is moving away from the pole is 1.6 times as much. So at the end, once we finally get to this, it's a simple question, simple implicit derivative included, but just 1.6 times 4, which is, let's see, 6.4. And the units, again, feet per second. But getting to that point is the tricky part. And figuring out what variables it's going to take, like where do I put the variables so that my equation isn't messy? Don't be afraid to like just say, oh, I don't like how that turned out. Let me start again. I know what the relationship is, but I don't want this to be a addition or subtraction, or I don't want this to be a division. I'm going to write it a different way. I'm going to define my variables differently so that I don't have to take a derivative of like dx minus a dt when x and a are both things. Like, wait, does that work normal? That looks a little strange. I don't like it. Because we have all these pieces that are related to one another, and you can write the same relationship in a variety of ways. So, in any case, streetlight question, it just turns out to be something about similar triangles, and the rate of moving within one triangle, just like the side lengths, is 1.6 times as much, or times smaller than, the rate of moving in the other triangle. So, let's see. Let's talk about then, if I can get this cleared. So in general, related rates just sum up. If we figure out what rates we've got, and we can figure out how the underlying quantities are related to one another, we can take a derivative of those quantities equation with respect to time, something that doesn't appear in it, and then relate instead of the quantities themselves, like distances in this case, the rates of change of those quantities. So on to some of our homework questions then. So I want to talk about number 9 first, which was the ladder. How do I make the shortest ladder that reaches over a fence to reach a wall on the other side? Because the diagram for it might look kind of like the question that we just did, but we're dealing with a different sort of problem. It's a minimizing, maximizing problem, in this case minimizing, optimization. And so the idea is that there's a building, doesn't really matter how tall the building is. There's a tall building, if I can get the, oh, that one, sorry. There's a building, there's a fence that is, what was it, 3 feet away, 6 feet away? Fence that was 6 feet away and 3 feet tall, so. And the idea is I have a ladder that I want to be able to reach from over here, over the fence, onto this wall someplace or another. So it doesn't matter, how tall this is. I just have to touch this, but I have to go over this fence. So I can't put it at any angle that I want. I have to put it at an angle so that it can touch the ground over here and then reach the building. And I want it to be somehow so that it is as short as possible. So I'm just going to draw a picture. Ooh, trying to make a straight line for a ladder. So if this 3-foot wall weren't here, I could obviously have a much shorter ladder because I could put this, just right up pretty close to the house like that, maybe only a foot away. But there's this whole 6-foot gap. I've got to be on the other side of that and still make it over a 3-foot wall. So I'm trying to make, in this case, a minimum ladder length. So somehow I've got to write an equation that expresses how long the ladder is relative to some other quantities in this diagram here. So let me call L the length of the ladder. And since we have other measurements in feet, I'll have the ladder length in feet. And we're going to try to minimize L. So rather than a related rates equation where we're going to take a derivative with respect to time, this ladder isn't moving anywhere. I could put it in different positions, in which case it would have to be different lengths. But I want to figure out the length that matches this one. So let's say that. Let's see, I've got L. Think about the same sorts of things as last time. L is a part of a large right triangle here that has a height that doesn't really matter what it is, but this side here, I'll call it X for a minute, would be one of the two sides that forms the right triangle with L in it. I've got a smaller right triangle where I do have a height mentioned, and, well, this length I don't have, but in terms of these two, I'm not going to have to worry about how much these are changing, so I don't really care if they're messy expressions or unmessy expressions for this little triangle. But if this whole length is X and that's 6, then I can call this X minus 6. And that's the length just from there to there. 6 feet is the rest of it. So the X minus 6 and 6 makes X. The reason I picked X for this whole length is so that it can be related to the length of this triangle. Now, we can write some expressions for similar triangles, but I don't want to worry about the hypotenuse here. That seems like that'd be kind of messy. So I'm just going to write an expression, even though it doesn't seem important. I don't care how tall the building is, but just where the ladder is, I'm just going to call this Y. How high up the building the ladder hits this. So in these notations here, X is being used as the distance that the base of the ladder is from the house building. And Y is being used as the distance up the side of the house that the top of the ladder hits. Let's see, so distance up the house, I don't know how you want to say that the top of the ladder hits. Sorry, words are kind of squishing together. So this x minus 6 here is just this distance that the end of the ladder is from the fence, the 3-foot tall fence or wall or whatever it was. But with all these pieces in here, I could use similar triangles, but I'm not trying to find a length. Like, I don't need to know how this is related to that. I need to find this length here. And I have a vertical side and part of a horizontal side of a triangle, and I'm trying to find something about a hypotenuse. I think I'm going to try something with Pythagorean theorem. So, because I want to write an expression for how long is the ladder. So the ladder would be square root of, a squared plus b squared equals c squared. This is the c, so square root of a squared and b squared. So x squared plus y squared. All right, so that's not particularly useful because it's got way too many letters, but x and y are related by the 3's and the 6's and by those similar triangles. So there are similar triangles involved, but not necessarily immediately. I want to find the length of the ladder, and the length of the hypotenuse I can get from the lengths of the sides. But x and y are related because of these 3's and 6's and all that sort of stuff. So again, in our smaller triangle, we've got 3 and x minus 6 as two sides here. And in the larger triangle, I've got y and x. So by using that same similar triangle's proportion, I should be able to relate x and y by writing a proportion here and solve for y in terms of x or x in terms of y. Since y only appears once, it'll look like it'll be easier to solve for y equals something with x. But let's see, 3 over x minus 6 equals y over x, or you want to write it a different way, you can. But if I want to solve for y, I could, this is equation relating x and y, but if I want to solve for y, I'm going to y times x minus 6 equals 3x, or y would be 3x over x minus 6. So y is the ratio here, where 3x isn't one of the things. 3x is this length times that length, but it came from cross multiplication of this proportion. So this looks kind of unpleasant, but it's an expression for y. And if I put it in here, then I can write the length of the ladder as a function of x instead of having just a formula for L in terms of x and y. Now, this becomes a little bit of an algebraic mess. 3x over x minus 6, quantity squared. Because here's an expression for the length of the ladder in terms of one independent variable, x. So any x that I pick would give me a different length for L that would be needed. Now x has to be greater than 6 because 6 is, part of x. So keeping that in mind, and it better not even be equal to 6, that would kind of cause problems. That would be a ladder straight up in the air. That's never going to work. But thinking about this equation, at this point we need to figure out where this has a minimum to it, and this is a weird square root of squared stuff equation with a rational function underneath included. That's kind of messy. Not something familiar like, oh, it's a parabola. So I know if I take the derivative, there's going to be one place where it's 0, and that's the vertex, and it's doing exactly what I want. This is a little bit less familiar sort of shape. You can graph this length function on GC and see what happens. Calculus-wise, though, I do want to go through how to solve this. It's not actually the worst thing ever. More difficult algebra-wise than what you'll see on your test. So keep in mind, your test is only 50 minutes, so I'm not going to give you problems that take 20 minutes of algebra to do. And also, in terms of that, some of the questions can be just like part of the process, like here's an equation that's already set up that models this length. How do I find, where does the maximum occur? Or here's a situation, which of the following, it is multiple choice, which of the following would be a function that we would need to use to optimize, to maximize or minimize the situation that was described? Or what is the goal of this problem? Are we trying to maximize length, minimize length, maximize height, something like that? So some of the questions related to optimization, and it's not all optimization, I was just giving several examples, can be just like a part of the process because I want to make sure that you understand the different pieces and not just can you do a whole problem through from start to finish, because that's a lot of stuff for a single multiple choice question. So that said, here's a function I'm trying to figure out where L of x is at a minimum. So calculus-wise, we want to figure out where L of x changes from decreasing to increasing, meaning where our derivative passes from negative to 0 back to positive, or a negative pause positive sort of situation. One thing to note here, just in terms of algebra, that could make this a little easier. It would come out if you did the whole thing anyway. But if I minimize L of x, this square root function, it would happen at the same place that L of x squared is at a minimum, meaning if the stuff underneath this square root sign is as small as possible, then the square root of it's going to be as small as possible. So what I'm actually going to do is just ignore the square root sign, because all that does is give us a denominator in our derivative that's, that over 2 times the square root of stuff. And a denominator of a fraction isn't going to help us make the derivative equal 0. That would tell us where it's undefined, which is not really what we don't want the derivative to be undefined, because that would be undefined when this is a square root of a 0, and you can see that, oh, that's not ever going to be 0. So that denominator wouldn't end up to be important. But if I square some quantity, if I take some quantity and minimize it, if I take its square root, that's going to be the minimum possible that the square root of that could be. So I'm actually going to L of x, the length squared, just the hypotenuse squared, would just be the stuff underneath, x squared plus this, just to make slightly fewer fractions in my algebra here. And if this is at a minimum, then so is that, because there's the way of square roots work. If I take a square root of a larger number, it's larger. If I take a square root of a smaller number, it's smaller. So just to simplify this a little bit, if I take a derivative of this then, with respect to x, I'm not just writing L of x squared derivative over here. So this derivative would just be 2x plus, I've got some work to do here, but it'd be 2 times this fraction to the first power times chain rule, derivative of that fraction. Well, that's quotient rule. Derivative of the numerator times the original denominator minus, other way around, derivative of the denominator, which is 1, times the original numerator, all over the denominator, x minus 6 squared. And you can see the numerator in this chain rule part is just, I've got 3x minus 18 minus 3x. So it's just negative 18. So what we have here, and give me a minute to erase some of this over here. Just get a little bit more room here. All right, so what I want to know is, where's this derivative? It's actually the derivative of the length squared. Where is this derivative equal to 0? Well, it looks kind of like a mess, but this part here is just negative 18 over x minus 6 quantity squared. And it's multiplied by a couple other things, a 3x over x minus 6 to the first power, and a 2. So I'm going to call this 6x over x minus 6. So if I put this all together, that looks a little bit less awful. And in fact, if I make common denominators, I can actually add those two. So I'm going to make this 2x times, here, this expression is x minus 6 cubed in the denominator. So if I have 2x over x minus 6 to the third power, and then this other term, oh, it's actually negative. Let's see, 18 times 6. I'm just going to write it as 18 times 6. Negative. All over x minus 6 to the third power. I want to know when this equals 0. And if I have two fractions added together that equal 0, that means they must be equal. You could multiply through by the denominator. That whole x minus 6 cubed goes away. And I just have a linear equation. 2x, oh wait, I didn't do this right, sorry. X minus 6 cubed, I was gonna say, that's way too simple. Sorry. 2x times x minus 6 cubed to give this a common denominator. I've got, let's see, 18 times 6 is, let's see, 30, 40, 50, 108. So I've got 2x times x minus 6 cubed minus 108x all over x minus 6 cubed equals 0. And multiply it through by x minus 6 cubed and equals 0. Or another way to think of that, if you have a single fraction and it's equal to 0, that means the numerator is equal to 0. So this looks like a mess, but I can factor out x from this. If I factor out x, I get, actually I factor out a 2x. 2x times x minus 6 to the third power. So it's a little fun with algebra, but it is doable. You don't have to use a calculator to get this, or a graphing calculator. Minus, 54 equals 0. Now it's factored. I can set each factor equal to 0. The first factor, 2x equal to 0, would mean x equals 0, which is not allowed. X can't be 0, it has to be at least 6. So it's not this part that's going to help. It's going to be the rest of this. X minus 6 cubed minus 54 equals 0, which means x is going to be the cube root of 54 plus 6. So just move over the 54, cube root, and add 6, rather than multiplying this out and getting a cubic equation in polynomial format. Sorry, this is slightly more than one page, but x minus 6 cubed would have to equal 54, which means x minus 6 is the cube root of 54, which means x is 6 plus that. But you can get decimal versions of that from just looking at this, here, that expression, figuring out when that's 0, or if you want to do what we did with the trig equation, with the pond obstacle, and say, oh, this looks awful, put it in GC and you can see. Now, for the test purposes, you can't use GC on the test. Please do bring a calculator unless you want to do, in case you want to do some computations like take a square root, or dividing by a weird decimal, or just not dealing with what on earth is 18 times 6 and accidentally messing up. So bring a calculator. It doesn't have to be fancy. You can't use a cell phone or GC, however. There aren't going to be questions this algebraically taxing, but I did want to go through this just so you can actually get to answers manually, and like as if it was 1800s and we don't have any calculators anyway. You can get these answers. It doesn't require technology, but technology is nice and we do have it in reality. But for the purposes of the test, they're going to be simpler algebraic problems, so you can do them manually if you want to, at least for the most part, other than maybe like computing the end, like, and what is the length of this shortest ladder? Oh, well, if x is 6 plus the cube root of 54, the length of the ladder is the square root of that squared plus, yeah, that's not something really to do by hand. But as I said, this expression is a lot more complex than what you'll see on the tests, but I hope that you had a chance to play around with it while you're doing your homework. All right, so sorry for that. It was a bit of an algebraic mess, but as I said, it's highly doable. So let's take a look at number 12, the cow problem. We had a nearsighted cow, and just one thing to note, I know I was talking with Emma about this in office hours the other day, but sometimes when you see problems like that, they're like, this is really bizarre, and it's like a really old looking picture. If you type in nearsighted cow on Google, you will see that problem done like 50 times. So with the same exact picture. It's from an old calculus book. I don't know what calculus book in particular. I think it probably says in the notes to the question in iMathAS. But we've got a cow who is standing near a billboard, and we're trying to maximize the angle available for the cow to see the billboard. So the diagram, if I can get this, let's see, actually I forget what the measurements are that were used, so let me open up your iMathAS stuff. Sorry. Alright, so on the stuff that was due Monday, the last question here. Rectangular billboard, 8 feet in height, stands in a field. Sorry, I will fix that. It's a field. So that its bottom is 11 feet above the ground, and a nearsighted cow with an eye level of 4 feet above the ground stands X feet from the billboard. We want to express that angle theta that's shown in the diagram in terms of X, and then find the distance that the cow needs to stand to maximize theta. So find the value of X that maximizes theta, so that they can see as much of the billboard as possible, I guess. So, in any case, in this diagram here, let me just write on this. We've got this X, let's see, that is something unknown, but the billboard is 8 feet tall. That's from top to bottom it's 8 feet tall, but the bottom is 11 feet above the ground, and the cow's eyesight is 4 feet above the ground. So this is not really to scale. This is at 4 feet tall. This is at a total height of 11, so this is an additional 7 feet in between there, and this is 8 feet here. Billboard's 8 feet tall, making the top of the billboard actually 19 feet off the ground, or 15 feet above the eye level of the cow. So, as I said, not really to scale, but we've got triangles. And again, we've got two interlaced triangles, but they're not similar triangles. We've just got, they share some pieces here. This X can be a part of two different right triangles, one that goes across from the cow's eyesight and forms this little triangle here to the bottom of the billboard, and one that goes to the top of the billboard. And theta then would be the difference in the two angles at the cow's eye. So if I think about this small triangle to the cow's eye, where this is not actually so small, it's 7 feet there, and this is X, and this is just this small angle here, I'll call it angle A, versus the largest right triangle we have here, which goes from the cow's eye level across and up to the top of the billboard. So this is still X. It's this full angle here. So that angle, I'll call it B. But the opposite side then is 15 feet long, from the cow's eyesight level up to the top of the billboard, which is 8 feet more than to the bottom of the billboard. So theta isn't in either of those triangles, but theta is the difference between this smaller angle and that larger angle. Or in other words, theta is B minus A in my notations here. And if B and A were something else, maybe like, oh great, I've got an equation. Now I've got theta in terms of B and A. Let me take a derivative, see where it's at 0 or undefined, and I'll find the maximum value of theta. Because my goal in this problem is to maximize the angle. So I want to write an expression or a function whose dependent variable is that angle. And I've got something like that. It's just a formula instead of a function. I've just got it's a relationship between theta and B and A, a couple other angles. But B and A can both be expressed in terms of X. Notice we are dealing with angles here, so this one does involve some trigonometry if we need to pull angles into this. So I want to relate A to 7 and X here using trigonometry. If this is the right angle here, what trig function would be the easiest to use that relates 7 and A and X? The two legs of the right triangle and a non-right angle? Tangent. Yeah, so tangent relates those three, or arctangent if I solve for the angle part. So I could think, oh, tangent of A, tangent is opposite over adjacent, if you want to think about that. So tangent of angle A is 7 over X. Or I could solve this for X, but that's not actually what I want. What I want to be able to do is write theta in terms of one variable. And there's no way I can just write this directly like, oh, A is like 7 times B or something like that. But I can rewrite A and B both in terms of this length X here. So if tangent of angle A is equal to 7 over X, then I can solve this for a by using the arctangent, inverse tangent function. This means the same as saying that a is the inverse tangent for certain angles of 7 over x. So it's just, it inverts the tangent function. So the input to a tangent function is an angle and the output is a ratio. The input to an inverse tangent function is a ratio and the output is an angle. So those are just inverses of one another. So this expression, regardless of how icky it looks, is an expression for a in terms of x, and I can certainly do the same with b. You can maybe see it's just going to be the same, only with a 15 in the numerator instead of a 7. So I've got then, let's see, arctangent or inverse tangent of 15 over x for b minus arctangent of 7 over x for a. So now I've got theta as a function of x. Now it's a messy function of x, but it is a function of x, so done. That was our first step. Write theta, the vertical angle subtended by the billboard at her eye, in terms of x, and then find the distance that the cow must stand from the billboard to maximize x. So find the value of, or to maximize theta, find the value of x that maximizes theta. So at this point, again, you've got technology options, you've got calculus options. The algebra is a little bit messy, but again, it's not awful. I just wanted to point out derivative stuff. Arctangent, that was the one of the trig functions that was not quite so horrible, one of the inverse trig functions. It's just that arctangent of x derivative was 1 over 1 plus x squared. So, well, we've got slightly messier things here, but if I want to take a derivative of theta with respect to x, I've got two terms. They're going to be similar terms. 1 over 1 plus x squared, well, it's 15 over x in this case, that gets squared. And then chain rule times the derivative of 15 over x should be negative 15x to the negative 2. Thinking about 15 over x as 15x to the negative 1 and taking a derivative of this. So I'm going to toss that 15x to the negative 1's derivative, just instead of as a second term here, I'm going to put it in the numerator to save a little bit of space. But times then negative 15x to the negative 2, or negative 15 over x squared. And same for the second term. Now this one has a subtraction in front of it. And then there's going to be a negative in the numerator also. Negative, it's just 7 instead of 15, but the rest of this is identical. So I want to know when this expression is 0 or undefined. It'd be undefined if x is 0 for sure, but x is not going to be 0. That'd be the cow standing under the billboard. It'd be impossible for the cow to see. That seems like it'd be nothing that makes any sense. So that undefined isn't going to help us. It's going to be a bad situation. X is probably supposed to be something greater than 0. You can maybe tell from the diagram in order for the cow to be able to see anything. So we're going to look for when this derivative is equal to 0. And it would involve a lot of, actually, no, if I want to go through all this, a lot of common denominators and multiplying some things out. But if I look at these fractions in just a slightly different way, this numerator is negative 15 over x squared. And the denominator is 1 plus, I'm just going to multiply that out, 225 over x squared. My other fraction, there's minus a negative, so I'm just going to call it plus 7 over x squared. And the denominator 1 plus 49 over x squared. Now, how I can make this a lot nicer is multiply through, I'm looking for when this derivative equals 0, multiply through the whole equation, both sides of it, by, multiply through by x squared. If I multiply everything through by x squared, so multiply by x squared over here, that gets rid of the x squareds in the numerator, or I can even think about multiplying each fraction by x squared over x squared. Multiplying by variables is generally to be avoided, but if I know that x isn't supposed to be 0, it's not a problem. So let me change colors for a second here. If I multiply by x squared over x squared, that should simplify things a bit. I'm going to do that to both fractions, but I'll just do it the quick way. I'm multiplying the left side by a form of 1, but that eliminates all these double fractions, and we just end up with then a numerator in the first fraction, negative 15, and a denominator, x squared plus 225. And in the second fraction, similarly, we get 7, and then the denominator, x squared plus 49. And this is still an ugly fraction that needs common denominators, but from here, I think it's maybe more doable. You could even, since it's two fractions added together equal to 0, you could split them on each side and cross multiply to solve to find this. So from here, it's not too messy, but we are about out of time, and I'm about out of space. But I did want to show you, you can simplify this a lot with just a couple little tricks. And I did want to talk about just, in general, tangent, trigonometry, those sorts of things. So over the weekend, eat food, enjoy time with your family, and when that's over, make sure you remember you've got 2 homework assignments. I'll see you again before this, but 2 homework assignments due Monday night, so if you have some spare time after you've done eating and shopping and footballing and everything else, take a look at those. One's on related rates, and the other's on implicit differentiation, and it's pretty short, but I will see you on Monday. Have a good long weekend.